Good morning, my dear students. Okay, coming to the numerical section. So we have the numerical problems in module 1, three topics. That is, first one is a principle of minimum potential energy, second one is a Rayleigh-Ridge method, and third one is a Gallagher method. Okay, so now today class I will tell you about the theory and what is the importance of minimum potential energy. So next class we will move on to the numerical problems on this minimum potential energy. Okay, so here first, what do you mean by minimum potential energy? Okay, so let me understand first potential energy means what. Okay, so as per this subject, so okay, that it is what is the potential energy? So it is defined as the sum of strain energy due to the internal stresses produced and the work potential due to the external forces is called as potential energy. That means here the strain energy nothing but it is already stored in the given element, that is the internal, so internal energy, and the work potential nothing but if the forces, external forces are acting on that element, then work done by the system is called as the external, that is work potential. Okay, the system which the work can be done with the help of the external forces we are going to call as work potential, and the strain energy is nothing but what, it is a store energy. Okay, the combination of both we are going to call as potential energy. Okay, and it is normally denoted as pi, capital Pi. Okay, so potential energy is equal to what, strain energy plus work potential. Just work potential, you understand that is the external forces, it is a stored energy, that is the internal energy. Okay, so in mathematical we are going to write as pi is equal to strain energy plus work potential. Okay, so this equation we are going to use to solve the numerical problems. Okay, so work potential is equal to what, pi, which is equal to strain energy plus work potential. Okay, is called as what, potential energy. Okay, so the next question is comes the displacement, that is what, minimum potential energy. So what do you mean by minimum potential energy? Okay, the principle state that of all the displacement configuration of a body can assume which satisfied the computability condition and boundary condition. Okay, the configuration which satisfied the equilibrium condition is one of which will have the minimum potential energy. Okay, so this condition is satisfied means we are going to call as minimum potential energy. That means here the read this, displacement configuration for body can assume which satisfy the computability condition. Means computability condition nothing but what, these are the mathematical condition which should be satisfied for the given the divided element. Okay, boundary condition means we are going to necessary conditions. Okay, wherever necessary is there we are going to apply. So computability condition nothing but what, these are the mathematical condition. Okay, so both the conditions are satisfied for the equilibrium condition, then we are going to call as such minimum potential energy. Okay, so same formula, that is the potential energy function which is equal to strain energy plus work potential. Okay, that is strain energy plus work potential. Okay, this is very important, they may ask you 2 more question, state the principle of minimum potential energy, and they may give one problem. Okay, so how to understand, explain the minimum potential energy means what. Okay, for the potential energies to be minimum, condition is this. Okay, so dou pi by, that is what, dou pi which is equal to delta is equal to strain energy plus delta work potential. Okay, so while solving the problem we are going to assume which is equal to 0. Okay, so look at this diagram. Okay, so here from the figure, two bodies having the same weight, okay, falling through a height, that is what, some height, that is h1, and weight 1 is h1 and weight 2 is h2. Okay, so both the bodies are satisfied for the boundary condition. Out of the two bodies, the body 2 has minimum potential energy because it falls through the lesser height. Okay, any body which is stable will have the minimum potential energy, this we have to remember this. Okay, so and we and the body 2 will have the minimum potential energy because it is falling through a lesser height for the stable equilibrium position. Okay, because of this condition the body 2 has what, minimum potential energy. Okay, so you have to write this. Okay, they may ask you state and explain the minimum potential energy means you have to write that principle, and you have to explain this diagram and this what explanation. Okay, so next one is one derivation will be there, we will derive this equation. Okay, so derive an equation for potential energy function for a 3D elastic body subjected to a point load, traction force, and body force. Okay, that is surface force. Okay, so that is point load, traction force, one more is what, work potential, body force, work potential force, and traction force. Okay, so we have to derive on these equations. Okay, so this is not important, but while solving problem you let me understand this, what you mean by point load, what you mean by traction, or it is also called as a surface force. Okay, and work potential force. Okay, so consider a 3-dimensional body, that is elastic body. What do you mean by 3-dimensional elastic body? So if you apply any body for the 3 elastic body, it will stretch. Okay, if you remove the force, then it will come original position. Okay, such type of body we are going to call as elastic body. Okay, so here consider a 3-dimensional elastic body of having a volume of V and subjected to a body force, surface, and point load. Okay, these three forces are acting on that particular element. Let U, V, and W be the displacement component in x direction, y direction, z direction. Okay, so we know the potential energy function is equal to what, strain energy plus work potential. Okay, so give equation number 1. So consider a small element for the 3D elastic body. So this is stress and this is strain. Okay, if you increase the Okay, so if you consider a small amount of stress, okay, small amount of body, that is a small amount of part from the given elastic body. Okay, if you apply more is the force, more strain. Okay, that is, look at here, if the strain energy of the body is given by area under the curve. Okay, so this is let us consider this is the area stress strain. Okay, so strain energy for this is equal to what, the half of stress into the strain and into volume. Okay, strain energy is equal to half of, this is the transpose of sigma t is nothing but what, sigma x, sigma y, sigma z, and the strain along with that direction. Okay, and into strain into volume of that particular volume. For a small element, the change in volume, that is v is equal to what, change in volume dv within a given body, we are going to consider as strain energy is equal to half of a transpose of sigma, that is stresses E into dv. Okay, so the entire body we are going to consider as what, if you apply integration, that is what, total energy, total strain energy, half of integration of V, that is strain energy into E into dv. Okay, this is the total strain energy present in the given body. So give equation number 1. Okay, like that you have to calculate. Okay, where sigma is equal to what, sigma x, sigma y, sigma z, and shear stress along xy and yz and zx. Okay, so this is about the strain energy induced in the given small element. Okay, so we have the definition, what we know the definition, strain energy plus work potential. We calculated only the strain energy, total strain energy on the given element. Along with that we need to calculate the work potential. Okay, total work potential on the given system. Okay, so if you take this, then we are going to see here how many total external forces are acting on this, how many, 3 forces. One is body force, surface force, one more is a point load. Okay, these 3 forces are external forces are acting on that element. Okay, so consider one by one. So work potential, that is work potential is due to what, external forces. Here in this body there are 3 external forces are acting, that is body force, surface, that is it is also called as a traction, and point load. Okay, body force it is denoted by F, surface force it is denoted by capital T, and point load it is denoted by capital P. Okay, so let me understand one by one. First case, K1, that is work potential due to body force. Okay, so for a small element, so work potential is equal to what, so I already told work done by the system is going to consider as negative sign here. Okay, so minus of f of x u plus f of y v plus f of z, that is z w into dv. So this is the work element along the x direction. Okay, f of x, f of y, f of z. Okay, so total entire body we are going to consider as, just take the integration. Okay, work potential is equal to minus of 0 to v f of x u plus f of y v plus f of z w into dv. Okay, so again if you modify this, work potential is equal to minus of integration of v capital U of t f into dv. So where U of t is nothing but what, this one, U of t is equal to u v w, and f is equal to f of x, f of y, f of z transport. Okay, so here f of x u means x displacement, u is the displacement along x direction, v is the displacement along y direction, w is the displacement for z direction. Okay, so this is the work potential due to body force. Like this you have to calculate the surface force and point load. Okay, so work potential due to traction of surface force, same for a small element, consider a small element. So work potential is denoted by what, traction force is denoted by capital T, so minus of into bracket T of x u plus T of v plus T of z w into ds. Okay, so change in surface area, ds nothing but change in surface area, here change in volume. Okay, so again so for the entire body is equal to, just put integration sign, minus of integration of v, that is a t of x u plus t of y v plus t of z w into ds. Okay, so again the total work potential, again just to remodify. Okay, so the work potential is equal to minus of 0 to s. Okay, u of t ts. Okay, t stands for traction of surface force, ds is equal to change in surface. Okay, give equation number 2. This is for due to surface force. Okay, similarly you calculate the work potential due to point load. Okay, work potential due to point load, here 3 forces are acting, that is minus of px u plus py v plus pz w. Okay, so u means displacement along x, v means displacement along y, w means displacement along z direction. Okay, again just to modify this, work potential is due to is equal to minus of u of capital U of t into p. Okay, so if the n number of forces acting on that particular element, means again the modification equations are equal to what, capital wp is equal to work potential is equal to minus of summation of ui t pi e. Okay, so give equation number 3. So that is 7, that is. Okay, now the total work potential due to external forces, you combine this all those, that is surface, traction, point load. If you combine all those equation, you are going to get this. Okay, work potential is equal to minus of integration of v u of t, this is due to body force, this is due to traction, and this is due to point load. Okay, so summation of, you are going to get this. Okay, now we got the total strain energy and the total work done on the system. Okay, now you put all these two equations, that is work potential and strain energy, in the equation number beginning equation, that is potential energy equation. Okay, so we got the function as potential energy of the function for a three-dimensional body is, you have to, this is the strain energy, this is a body due to external force. Okay, so this is the equation what we are going to call as total potential energy of the function. Okay, this function is required to solve the numerical problems. Okay, so potential energy function pi is equal to half of overall entire body, that is integration of sigma t strain dv minus of, this is due to traction force, that is what, this is due to the body force, this is due to traction force, this is due to point load. Okay, so this equation give number 1, and this equation is called as what, the potential energy function for a 3D elastic body, that is, it is the expression for potential energy function for a three-dimensional body. I think you understand this. Okay, it is nothing, just you understand here, potential energy function is equal to strain energy plus work potential. Calculate the total strain energy on the given system, that is 3D elastic body, and calculate the total work force, that is work potential on the given body combined, that will gives what, this equation. Okay, so here in the external force are acting 3, body force, traction, and this what, point load. Okay, this is the work potential, this is the strain energy. So total you are to use what, potential energy function. Okay, so like this you have to derive this equation. Okay, so here just to remember that, so potential energy is nothing but what, strain energy plus strain energy plus work potential, that is called as principle of minimum potential energy. Okay, so I hope you understand this. Okay, thank you.